Why do 5 specific cars from the 1990s still run reliably today, while modern cars are designed to fail? Why does a 30-year-old sedan often feel more solid than a brand new luxury vehicle? In this video, we will examine 5 machines that defy planned obsolescence: a Japanese flagship, a German executive fortress, an overlander's truck, a Swedish brick, and an American workhorse. Each one reveals a different philosophy of durability. We are talking about engineering so robust that the engine from our first subject was actually approved by the Federal Aviation Administration for use in aircraft. To understand why they never broke, we must look at a lost philosophy called pre-optimization. Modern design relies on finite element analysis to calculate exactly when a part will fail, shaving material down to the absolute limit. It is efficient, but leaves zero margin for error. Engineers used to build components twice as strong as necessary, just in case. That inefficiency created accidental immortality, simply because the tools to perfectly underbuild cars did not exist yet. Fueled by the Japanese asset bubble, unlimited capital forced European rivals into an arms race of quality. For a brief window, technical directors overruled accountants, prioritizing perfection over profit. The first subject is the machine that forced the entire industry to spend billions in a panic. The story begins in August of 1983 with a secret meeting. The chairman of Toyota, A.G. Toyota, gathered his top strategists and issued a challenge that would fundamentally alter the luxury automotive landscape. The project was codenamed Circle F, which stood for flagship. The mandate was terrifyingly simple, yet technically contradictory. They were to build a car that was better than the best vehicles in the world. It had to be faster than a BM, quieter than a Jaguar, and more aerodynamic than a Mercedes-Benz. Crucially, there were no constraints on the budget or the timeline. It was a project with a blank check. The scale of human capital deployed for this single vehicle was unprecedented in automotive history. The development team included 60 designers, 2,300 technicians, and over 1,400 engineers. They were split into 24 different teams, each focused on a specific aspect of the vehicle. While a typical car development cycle might cost $300 million and take 4 years, the Circle F project ran for 6 years. The total cost exceeded $1 billion in 1980s currency. This was an astronomical sum that was only possible because of the rampant liquidity of the Japanese economy at the time. To ensure the car would meet the impossible standards set by the chairman, the team built approximately 450 full-scale prototypes. This was triple the industry standard. They did not just test these cars, they tortured them. The prototypes were driven for nearly 3 million kilometers across deserts, highways, and alpine roads. The obsession with perfection extended to the smallest details. The engineers focused heavily on tolerances. They utilized laser brazing technology to weld the body shell, a technique that allowed for continuous seams rather than the spot welds used by competitors. This significantly increased the rigidity of the chassis. The panel gaps were engineered to tolerances that were previously thought impossible for mass production, often measuring less than 3 millimeters. This was not merely for aesthetics. Tight and consistent gaps reduced wind noise and prevented moisture from entering the door jambs, which protected the body hardware from corrosion over decades of use. The most famous demonstration of this engineering precision was the champagne glass commercial. In the advertisement, a pyramid of crystal champagne glasses was stacked on the hood of the car, while the engine accelerated to the equivalent of 145 miles per hour on a dynamometer. The glasses did not move. The champagne did not ripple. This was not a camera trick or marketing fluff. It was a factual display of harmonic cancellation. The engine was so perfectly balanced that it transmitted virtually no vibration to the chassis. This meant that the motor mounts, exhaust hangers, and sensor connectors were not subjected to the constant low-frequency shaking that degrades components over time. The car was designed to resolve what the engineers called the Lexus contradictions. It had to be capable of high speeds, yet remain whisper quiet. It had to be heavy with technology, yet fuel efficient. To achieve this, they needed to create a mechanical heart that was virtually indestructible. If the Lexus LS400 was the ambitious challenger, the Mercedes-Benz W124 was the defending emperor. Produced primarily from 1984 to 1995, this mid-size sedan hails from a specific era when Daimler-Benz operated under a unique corporate hierarchy. It is often said that during this time, the engineers told the accountants what the car would cost, rather than the accountants telling the engineers what they could spend. This was an engineering dictatorship in the purest sense. The W124 was not merely a new model year update, it was a foundational architecture for the brand. Its development budget is rumored to have exceeded 2.5 billion Deutsche Marks. This staggering sum, comparable to the gross domestic product of small nations at the time, was invested not in marketing campaigns, but in fundamental metallurgy, suspension kinematics, and crash safety. The goal was absolute dominance of the executive sedan market through technical superiority. The result was a vehicle that earned the metaphor of a bank vault. This description refers to the way the heavy steel doors close with a mechanical finality that is largely absent in modern vehicles. The construction utilized extensive computer simulation and high-strength steel to ensure the body was rigid. This stiffness meant the car did not loosen up, rattle, or crack even after years of driving on rough roads. It utilized heavy, solvent-based paints and lead-based primers that were incredibly durable and resistant to chipping. This was before the environmental mandates of the mid-90s forced manufacturers to switch to water-based paints, which never quite matched the longevity of the old chemical formulas. The undercarriage was coated in a thick, PVC-based sealant that protected the galvanized steel panels from road salt. The interior was designed with a similar philosophy of indefinite service. The materials were chosen to withstand decades of use as taxicabs in Germany. The switches, buttons, and seats were not designed to look flashy in a showroom. They were designed to resist wear. A window switch in a W124 can be disassembled and repaired rather than replaced. The plastic and alloy fittings were thick and substantial. The car was deliberately constructed as a long-term asset, not a disposable commodity. Mercedes engineers in this era were famously conservative. If they calculated that a part needed to last 250,000 kilometers, they might specify it to tolerate twice the stress it would ever actually see. This approach stands in sharp contrast to what followed. The transition from the W124 to the W210E class in 1995 is the most dramatic example of the industry-wide shift toward cost-down manufacturing. Under new leadership and the influence of the Lopez effect, the successor model was mandated to be significantly cheaper to build. The result was the use of thinner steel and those new water-based paints, leading to rust issues that plagued the later models. The W124 remains the last expression of the cost, no object philosophy. It was a machine built to a standard, not a price point. However, the solidity of the body was only half the equation. To truly understand why this car is still ubiquitous in developing nations, one must look at the specific technical innovations that defined its ride and its powertrain. While the engineers in Stuttgart and Aichi were refining the luxury sedan for the Autobahn, a different kind of durability was being forged for the places where roads did not exist. In 1990, Toyota released the 80 Series Land Cruiser. It arrived at a critical juncture in the history of the sport utility vehicle. Before this moment, four-wheel drive vehicles were largely agricultural tools, uncomfortable, loud, and crude. After this moment, they would become suburban status symbols. The 80 Series sits right in the middle. It is the bridge between the tractor and the limousine, capturing the perfect balance of utility and comfort before the segment softened. The design brief for the 80 Series differed from any other passenger vehicle on Earth. Toyota's internal engineering standard for the Land Cruiser is a 25-year service life in severe off-road conditions. This does not mean the car is expected to last 25 years in a heated garage. It means it is engineered to survive a quarter of a century in the Australian outback, the African savanna, or the humid jungles of Southeast Asia. This specific requirement meant that mechanical failure was not viewed as an inconvenience. In the environments where this vehicle was destined to serve, A breakdown could be a life-threatening emergency. This is why, for decades, the 80 series became the standard vehicle for the United Nations, the Red Cross, and remote non-governmental organizations. When you see news footage from the 1990s of humanitarian missions in conflict zones, the white vehicle in the background is almost invariably a Land Cruiser. The secret to this survival lies in the chassis. While modern SUVs have moved to unibody construction to save weight and improve fuel economy, the 80 series retained a separate body-on-frame architecture. But not all frames are created equal. Most pickup trucks use what is called a C-channel frame, which is open on one side. This allows the frame to flex and twist under load. The frame rails of the Land Cruiser, however, are fully boxed. They are enclosed rectangular tubes of heavy steel. This boxing provides immense torsional rigidity, preventing the frame from twisting, even when the vehicle is traversing deep ruts or climbing rocks. The steel used in these rails is significantly thicker than standard automotive sheet metal. In critical stress areas, the steel is estimated to be between 4 and 5 millimeters thick. This allows the chassis to withstand repeated impact loads that would crack a lighter frame. It is effectively a piece of heavy industrial equipment disguised as a family car. This robust foundation allowed Toyota to make a controversial decision regarding the suspension. The engineers retained rugged solid axles for both the front and the rear. A solid axle is mechanically simpler and more durable than independent suspension. It protects the delicate drive shafts inside a thick steel housing, shielding them from rocks and debris. However, to meet the rising demands for comfort, they replaced the harsh leaf springs of the previous generation with long travel coil springs. This was a revelation. It provided a ride quality that was acceptable for luxury buyers while maintaining the massive axle articulation required for extreme off-roading. It was a compromise that satisfied everyone, creating a vehicle that could cruise comfortably on the highway at 70 miles per hour and then immediately cross a desert without modification. But a chassis is just dead weight without the force to move it. And the powertrain selected for this expedition machine was equally committed to the philosophy of isolation and endurance. While the engineers in Japan were fusing luxury with utility, a small manufacturer in Sweden was taking a very different approach to durability. By 1990, Volvo did not have the massive research and development budgets of Toyota or Mercedes-Benz. They could not afford to design a completely new car from scratch every few years. Instead, their strategy was evolution rather than revolution. The Volvo 940, produced from 1990 to 1998, was effectively the final and most perfected iteration of a platform that had been introduced nearly a decade earlier. It was the ultimate evolution of the architecture known affectionately as the Swedish brick. This car was not designed to be cutting edge. It was designed to be the safest and most logical form of transport on the road. The philosophy was one of evolutionary safety. Because the engineers had been refining this same rear-wheel drive chassis for so long, every potential flaw had been identified and rectified years before the first 940 rolled off the assembly line. The structure of the car was built around the concept of a safety cage. The 940 was one of the first cars to feature the side impact protection system, known as SIPS. This was not merely an airbag system. It was a fundamental restructuring of the unibody. Engineers installed high-strength transverse steel rails in the floor and reinforced the roof rails and pillars. While the primary purpose was to protect occupants during a crash, this reinforcement had a secondary benefit that contributed to the car's immortality. The structural stiffening required for safety made the chassis incredibly rigid. This rigidity allowed the car to resist the twisting forces that cause metal fatigue over time. The energy distribution philosophy meant that loads were spread across the entire chassis, preventing stress cracks from forming at suspension mounting points. The car felt solid because it was structurally unified in a way that lighter, more modern cars were not. The longevity of the body was further ensured by an obsession with corrosion resistance. Volvo utilized a zinc bath galvanization process for the 940. The steel bodies were dipped in zinc before being painted. This zinc coating acts as a sacrificial anode. If the paint is chipped by a stone, the zinc oxidizes instead of the underlying steel, preventing rust from taking hold and spreading beneath the paint surface. Combined with a thick, rubberized undercoating applied at the factory, these cars became nearly immune to the road salt that dissolved lesser vehicles. The aesthetic of the car followed its function. The boxy shape was not a stylistic failure, it was a functional choice. The upright glass provided unparalleled visibility, and the square cargo area offered more usable space than larger, curvier vehicles. It was a design that rejected the aerodynamic trends of the 90s in favor of pure utility. But the true heart of the Volvo legend was not the body, but the engine that pulled it. Under the hood lay a piece of iron so durable that it spawned a cult following of its own, a mechanical device that turned a safe family sedan into a candidate for the million-mile club. Across the Atlantic, the American automotive industry was taking a different approach to longevity. While the Europeans were refining unibody construction, Ford was doubling down on a design that dated back to the 1970s. The Ford Crown Victoria, specifically the second generation introduced in 1992, was built on the legendary Panther platform. By the 1990s, this architecture was a dinosaur. It used body-on-frame construction, a layout where the body of the car sits on top of a heavy steel ladder frame, separated by rubber mounts. This was the way cars were built in the 1950s, and by the 90s almost every other sedan had moved to lighter, more efficient unibody designs. For the specific purpose of durability, the body-on-frame layout offered immense advantages. It made the Crown Victoria uniquely suited for the abuse of fleet service. In a unibody car, a moderate collision often bends the entire structure, totaling the vehicle. In a Crown Victoria, the frame absorbs the impact. If a fender, door, or bumper is smashed, it can be unbolted and replaced without compromising the structural integrity of the chassis. This modularity meant taxi fleets and police departments could keep these cars in service indefinitely, repairing damage that would send a modern sedan to the crusher. The ultimate expression of this industrial durability was the P71 Police Interceptor package. These were not just standard cars with flashing lights. They were upgraded for severe duty. The cooling system was massive, designed to keep the engine at operating temperature even while idling for hours in the blistering heat of an Arizona summer. The hoses were green silicone, a material chosen because it does not degrade or crack over time like standard rubber. The suspension was reinforced with heavy-duty springs and shocks designed to withstand jumping curbs at speed. Under the hood sat the 4.6-liter modular V8 engine. While it was technologically advanced for its time, featuring overhead cams, it was tuned for longevity rather than performance. The engine produced relatively low horsepower for its size, meaning the internal components were never stressed. A large V8, producing only 250 horsepower, is operating at a fraction of its potential. This low specific output meant the pistons, rods, and bearings were subjected to minimal force, allowing the engine to run for hundreds of thousands of miles without a rebuild. To refine the handling of this heavy live axle beast, Ford engineers installed a Watts linkage in the rear suspension. This mechanism consists of two rods connected to a center pivot point on the axle. It physically forces the rear axle to remain perfectly centered under the car, preventing the side-to-side movement that plagued older American cars during cornering. It was a piece of sophisticated geometry applied to a crude suspension design, providing stability without sacrificing the ruggedness of the solid axle. The result was a vehicle that felt like a boat but was built like a tank, a machine that became the backbone of American law enforcement because it was simply too tough to die. The common thread binding the Lexus, the Mercedes, the Land Cruiser, the Volvo, and the Ford is the logic of pre-optimization. They were all constructed with massive safety margins that made little financial sense. By the mid-90s, the industry underwent a radical shift. A philosophy known as the Lopez effect began to permeate the boardrooms of automotive giants. Named after a procurement executive who became famous for ruthlessly slashing supplier costs, this approach prioritized immediate profitability over long-term reputation. Manufacturers realized that building a car to last 20 years was fundamentally bad for business. If a vehicle never breaks, the customer has no incentive to replace it. At the same time, the nature of the automobile changed. The introduction of complex CAN bus networks and proprietary software introduced the concept of digital obsolescence. A mechanical fuel pump can be rebuilt by a machinist in 100 years. A proprietary microchip cannot be replicated once the factory closes. The industry focus shifted from ensuring durability for the third owner to ensuring reliability for the first owner. The goal became to make the car feel perfect for the duration of a 3-year lease. What happened after the warranty expired was no longer the engineer's concern. Safety regulations also played a role. To meet crash standards, cars had to become lighter and softer, designed to crumple rather than resist. The heavy iron of the 90s was replaced by high-strength alloys and plastic composites. The era of the over-engineered machine ended not because we forgot how to build them, but because the industry decided they were simply too expensive to keep alive. The accountants finally won the argument against the engineers, and the concept of the forever car vanished into the history books. These 5 machines represent the fleeting moment when the engineers actually won the argument against the accountants. Driving them today offers a specific sense of a heft and purpose that modern manufacturing has simply failed to replicate. If you have a story about a high-mileage survivor from the 90s, share it in the comments below. If you appreciate this history of design and craftsmanship, make sure to subscribe for more stories.